Assalamualaikum and welcome to the video. I am Muhammad Hafizul Hafiz bin Husin from Physics Unit KMPK. I would like to welcome you to the video series and most important of all, welcome to this amazing college. In this video, we are going to go through Experiment 1, Measurement and Uncertainty. Make sure you have your jotter and manual ready. You will need your jotter for taking notes as you follow along with the video. The learning outcome of the experiment is that you can measure and determine the uncertainty of physical quantity. Uncertainty or doubt of measurement can be understood as follows. Let's say you are trying to measure the length of the leaf. The ruler has a resolution of 0.1 cm. Resolution is the smallest increment of the measuring instrument or the smallest division on the scale. What would be the length of the leaf? You are sure that the leaf is at least 3.5 cm. You are pretty confident on that. But as you can see, the end of the leaf is not exactly at the 3.5 cm mark. We cannot really tell for certain the length of the leaf. So we are going to estimate the length of the leaf. We estimate the length to be about 3.5 cm. The reading is actually at the interval between 3.5 and 3.6. This interval is the uncertainty of measurement. We are going to report the length of the leaf as 3.5 plus minus 0.1 cm. So when other people see the reading, they know the value are estimated closest to 0.1 cm. So, when reporting the measurement, we will write the value of the measurement as our best estimate plus minus the uncertainty. If x is the measured physical quantity, then the value of x is written as x plus minus delta x. The delta x is the uncertainty of the value of x. So, every measurement that we make in the experiment has some degree of uncertainty. As we have shown before, the uncertainty is due to the limitation from the resolution of the measuring instrument. Instrument with better resolution is able to produce measurement with higher precision. For example, if we take the vernier caliper, the resolution is 0.002 cm. If the caliper is used to measure the length of the leaf instead of the meter ruler, the reading will be much more precise and we will have a much lower uncertainty. The uncertainty is going to be 0.002 cm. According to Stephanie Bell, the uncertainty tells about the quality of the measurement. You can pause the video and you can read the definition given by Stephanie Bell on uncertainty of measurement. I hope this has given you some ideas on what uncertainty is and why it is very important when making and reporting measurement. Coming back to the learning outcome, now I am going to show you how to determine the uncertainty of measurement. We are going to discuss how you can determine the uncertainty for 1. Single reading, 2. Repeated reading, and 3. Combination of uncertainty for a derived quantity. Moving on to the first section, uncertainty of a single reading. The uncertainty of measurement is determined from the method of reading. Either you have a single point reading, 2-point reading, or vernier scale reading. For single reading, the uncertainty of measurement is taken as half of the smallest division on the scale. Example of the instrument are ammeter, voltmeter, and thermometer. For a 2-point reading, the uncertainty is taken to be 2 times half of the smallest division, which is going to be equals to the smallest division from scale. Example of instrument are meter ruler and protractor. Finally, we have vernier scale. The uncertainty is going to be the smallest unit on vernier. Example of the instrument are vernier caliper, micrometer screw gauge, and traveling microscope. The easy way to know whether you have a single point or double point reading is that if the zero of the instrument is automatically lines up, means that the instrument is going to give you a single point reading, as in the case of a voltmeter. If you look at the resolution of the voltmeter, the resolution is 0.1 volt. The uncertainty is half of the smallest division, so the uncertainty of the instrument is 0.05 volt. If you have to manually align the zero, means that you have 2-point reading. If you look back at the examples where we are trying to determine the length of a leaf, first we need to align one end of the leaf with the zero on the meter ruler, and then we have to estimate where the other end of the leaf on the scale. In this case, the estimate is made twice. That is why uncertainty is 2 times the smallest division from scale. Here are some of the examples of the instrument. Let's look at meter ruler and ammeter. Meter ruler is 2-point reading. The resolution is 0.1 cm. The uncertainty for measurement for the meter ruler is 0.1 cm, which is equals to the resolution of the instrument. In the case of the ammeter, the zero is automatic. Thus, we have a single point reading. The resolution is 0.02 milliamps. The uncertainty of the instrument is half of the resolution, 0.01 milliamps. For vernier and micrometer screw gauge, the uncertainty is just going to be equals to the smallest unit on the scale. We recommend that when you write the list of the apparatus, go to the measuring instrument in the list and write the range and the resolution of the instrument next to the instrument name. You can get both of the value from the instrument itself. Here are some examples. Next to the instrument, we write the range and the resolution of the instrument. Look at how the value of the length of the book and the current is written. The measurement value and the uncertainty has the same decimal point. The percentage of uncertainty can be calculated as the relative uncertainty, delta x divided by x, this is the relative uncertainty, times with 100%. Relative uncertainty times with 100% will give you the percentage of uncertainty. We want the value to be small. Remember when I said uncertainty tells about the quality of measurement. The smaller the value of the percentage of uncertainty, the better the measurement. That is it for a single reading measurement. Now we are at the repeated reading section. We want the uncertainty of the measurement to be small. In order to do that, we are going to do a repeated reading. In repeated reading measurement, the value of the measurement is the average value of the reading plus minus the uncertainty. This two formula is going to be used to find the average value and the uncertainty of reading. I'm going to show you some examples on how to use these two formula. In repeated reading, we are going to use table to record the value of the measurement. On the left, we have reading from an ammeter. The uncertainty of measurement is recorded at the very top of the current in circuit column. The value of the uncertainty is 0.05 ampere. This is for single reading uncertainty. To better improve the uncertainty, we repeat the measurement of current 5 times. First, we calculate the average value of current. We add all the value from the reading and then divide by the number of readings. We get the average value of current to be 1.54 amps. Next, we want to calculate the uncertainty for the measurement. We are going to use this formula. On the third column, we find the difference between the average value with each of the reading. And then we add all them up and then divide by the number of reading. This gives us the uncertainty for the current. We get the value of 0.032 amps. For the uncertainty, we have to round up the value to one significant figure. You have to remember this rule. So the uncertainty of our repeated readings is 0.03 amps. This improves the uncertainty of our reading from 0.05 to 0.03. The percentage of uncertainty can be calculated using this formula. 0.03 divided by the average value of the current and then times 100%. The percentage of uncertainty that we get is 1.94%. Okay, now we are on the section of combination of uncertainty. Previously, we are only discussing the uncertainty of base quantity measurement. In this section, we are going to look at how the uncertainty propagates into calculation. We are going to look at the uncertainty for derived quantity. I'm going to present some example on how to calculate the uncertainty for a derived quantity. If the measured value is used for addition or subtraction, for example, we have x equals to a plus b minus c, the measured value of a, b, and c has its own uncertainty, delta a, delta b, and delta c. The uncertainty for the value of x is just the sum of the uncertainty of a plus b plus c. To illustrate the idea of the combination of uncertainty for addition and subtraction, we are going to use this example. In this example, we are going to find the parameter of parallelogram. The size is measured to be 5.0, 13.0, 4.30, and 10.03. The parameter can be calculated by adding all the sides. 5.0 plus with 13.0 plus 4.30 plus 10.03, this gives us 32.33 centimeter. The addition rule for significant figure is that the number of decimal in the result cannot exceed the lowest number of decimal in the measurement. The lowest decimal in the measurement is the 5.0 and 13.0. They only have one decimal. So, the final answer must only have one decimal. We are going to round off the value to 32.3. The uncertainty for the parameter is going to be the sum of all the uncertainty. 0.1 plus 0.01 plus 0.1 plus 0.01. We get 0.22. When writing the final answer, we have to make sure the decimal point of the parameter and the uncertainty are the same. The parameter of the parallelogram is 32.3 plus minus 0.2 centimeter. Now we have a multiplication by a constant. The value of x is obtained by multiplying the constant k to the value of a. Value of a is a measured value. The uncertainty for the value of x is going to be the constant times the uncertainty of a. In this example, we have a circle with a radius measured to be 2.0 plus minus 0.1. The diameter of the circle is 2 times the radius of the circle. So 2 times 2.0 is 4.0 centimeter. The uncertainty for the diameter is just 2 times the uncertainty of the radius. So we have 2 times 0.1 equals to 0.2 centimeter. So the value of the diameter is 4.0 plus minus 0.2 centimeter. When writing the answer, make sure the value and the uncertainty have the same decimal. Now, we are going to find the combination of uncertainty for multiplication and division. The way we are going to find the combination of uncertainty for multiplication and division is very similar to addition and subtraction. But instead of adding the uncertainty directly, we add the relative uncertainty. In this case, we have x equals to a times b over c. The combination of uncertainty for x is delta a over a plus delta b over b plus delta c over c. The combination of uncertainty for multiplication and division can be calculated as the sum of the relative uncertainty for a, b and c. Or you can add the percentage of uncertainty of a plus b plus c. Remember, percentage of uncertainty is just relative uncertainty times with 100%. In this example, we are going to find the area of a rectangle. The sides are 10.0, it has 3 significant figures, and the other side 4.0, it has 2 significant figures. Thus, the final answer must be rounded off to 2 significant figures. The rule for significant figure for multiplication, the answer must have the fewest number of significant figures as the number we started with. The area of the rectangle is 40 centimeters square. 10.0 times with 4.0. We first calculate the relative uncertainty for area. The relative uncertainty for multiplication is just the sum of the individual relative uncertainty. Thus, we have the delta x over x plus delta y over y. This gives us the relative uncertainty of 0.035, or in the percentage uncertainty as 3.5%. To get the uncertainty for area, we multiply the relative uncertainty with the area. 0.035 times 40, we get 1.4. The area and the uncertainty for area must have the same decimal. So we have to round off the value of the uncertainty to 1. The area of the rectangle is 40 plus minus 1 centimeter square. Raising a measurement to a constant power. In this case, we have x equals to a to the power of n. The relative uncertainty for x is just equals to n times the relative uncertainty for a. In this example, we have a cube with a measured sides of 2.0 plus minus 0.1 centimeter. The volume is just equals to the side d cube, d times d times d. So the volume of the cube is just equals to 2.0 cube equals to 8.0 centimeter cube. Remember, for multiplication, the number of significant figure in the result must not exceed the number of significant figure in the measurement. D cube is d times d times d. Because d is repeating 3 times, we are going to add the relative uncertainty for d 3 times. Hence, we can just multiply the relative uncertainty of d by 3. This gives us the relative uncertainty for the volume equals to 0.15 or 15%. Thus, the volume of the cube can be written as 8.0 plus minus 15% centimeter cube. To get the uncertainty for the volume, the relative uncertainty times with the volume. We get 1.2 centimeter cube. Thus, the volume of the cube is 8.0 plus minus 1.2 centimeter cube. We are going to do another example. In this example, we are going to find the volume of a sphere. The equation of the volume of a sphere is equals to 4/3 pi r cubed. The radius is raised to the third power. Using the equation, we get the volume of sphere equals to 64.4498. We are going to round off this value into two significant figures. We have 64 centimeter cube. Then we find the relative uncertainty for the volume. We can ignore the constant in the calculation of the relative uncertainty for the volume. Because R is repeating 3 times, so the relative uncertainty of volume is 3 times the relative uncertainty of the radius. We get the percentage of uncertainty for volume equals to 0.12 or 12%. To find the uncertainty of volume, we multiply the percentage uncertainty or the relative uncertainty of volume with the volume of the sphere. 0.12 times 64, we get 7.68. We round off the value to 8 so that the volume and the uncertainty have the same decimal. The volume of the sphere is 64 plus minus 8 centimeter cube, or we can write the volume as 64 plus minus 12%. The procedure has 3 sections. In the first section, you are going to do a single reading, and then followed by a repeated reading, and finally you are going to calculate the derived quantity and its uncertainty. Before I end the video, I am going to summarize the procedure of the experiment in this table. For single reading measurement, you are going to measure the length and width of the manual, the length of the rod, and mass of ball bearing. In the repeated reading measurement, you are going to measure the external diameter of rod, the diameter of a coin, and the diameter of ball bearing. You can use this table to record your measurement, one table for each item. In the derived quantity calculation, you are going to calculate and determine the uncertainty for the derived quantity. You are going to calculate the perimeter of manual, circumference of coin, and finally, the surface area, the volume, and the density of the ball bearing. You have measured all the base value to calculate the derived quantity in the previous section. Use the appropriate formula to find the value of the derived quantity. That is it for the video. Thank you so much for your attention, and see you in the next video.